In the last two screencasts, we discussed different ways of describing the change in a variable. We've talked about total change and percent change. In this screencast, we discuss a third approach, namely growth and decay factors. Suppose that a variable v starts at a value v1 and increases or decreases to a value v2. The number r, for which v1 times r is equal to v2, is called the growth factor or decay factor. So you have this variable v, and its starting value is v1, and its final value after changing is v2. We could ask, how many times larger or smaller is v2 than v1? In other words, if I start with v1, what number would I need to multiply v1 by in order to get v2? Written as an equation, I would say v2 is r times the size of v1. The number r is what we call a factor because it's multiplied by v1. R sometimes represents the growth in a variable. It sometimes represents a decrease in the variable. And so we refer to it as either a growth factor or a decay factor. Let's go ahead and look at our first example. Suppose the size of a bacteria colony was originally 60. So 60 is our starting value, that's v1. Determine the size of the colony now. So in other words, we're trying to find the final value of the variable. In part A, we're told that the size of the colony changed by a factor of 2. In other words, r is 2. So v2 in this example would be 2 times v1, which is 60. So we arrive at 120. So in other words, when r is 2, the colony doubles in size. That's something to remember. A factor of 2 means that a quantity has doubled. Let's look at part B. Here, the size changed by a factor of 1.3. This means the final size of the colony is 1.3 times the size of the colony originally. If we multiply these, we arrive at 78. Let's look at part C. Here the size of the colony changed by a factor of 0.75. So in other words, the final value of the size of the colony is 0.75 times the original size of the colony. If we multiply these, we get 45. Now, it's worth noting here that the colony decreased in size. This is different than what happened in parts A and B, where the colony grew. In part D, the size changed by a factor of 0.05. So the ending size of the colony is 0.05 times the original size of the colony, which, if we multiply this, gives 3. So again, the size of the colony has decreased, and in part D, it's decreased significantly, from 60 down to 3. Let's go ahead and look at these next two examples. Example 2.14. Suppose the variable x increases in value from 12 to 48. by what factor has the value of x changed? So in this example, you are being given the starting value of the variable and the ending value of the variable, and you are trying to determine the factor. So we're told the starting value is 12. So we have 12. We know that 12 gets multiplied by some factor, and when we're done, the ending value of the variable is 48. The question is, what is the value of the factor? In this case, it's not hard to see that the factor has to be 4, because 48 is 4 times 12. So in this case, the variable x increased by a factor of 4. Let's look at example 2.15. Suppose a variable x decreases in value from 30 to 24. By what factor has the value of x changed? Again, our goal is to determine the factor. We've been given the starting and the ending values. The starting value is 30. We multiply that by some factor, and we know that in the end we're supposed to arrive at the ending value, which in this problem is 24. To determine the factor in this case, we take 24 and divide by 30. If we work that out on a calculator, we arrive at 0.8. So 24 is 0.8 times 30. Or said another way, the variable x decreased or changed by a factor of 0.8. Before going on to the next page, it's worth stopping here and making a few observations based on these examples. First of all, notice that if you have a factor that is larger than 1, for example, the 2 and the 1.3, notice that this corresponds to growth in a variable. Here, the variable increased from 60 to 120. Here, the variable increased from 60 to 78. This is due to a factor that is larger than 1. If a factor is smaller than 1, as in these two parts, this corresponds to a variable that's decreasing. In parts C and D, the variable decreased from 60 down to 45 and then down to 3. Again, this corresponds to a factor that is less than 1. A second observation can be made from looking at the bottom two examples. In these two examples, you are given the starting and the ending values of a variable, and you're asked to determine the factor. Notice that you can still use this equation to determine a growth or decay factor, but you need to rewrite the equation differently. You need to solve it for r. In this case, r would have to equal v2 divided by v1. In other words, the factor is equal to the ending value of v divided by the starting value of v. This is precisely what we did right down here. We took the ending value and divided by the starting value of v in order to arrive at our final value of r. Let's go ahead and summarize. Growth of a variable corresponds to a factor larger than 1, while the decay of a variable corresponds to a factor less than 1. If the starting and ending values of a variable are known, then the growth and decay factor can be calculated as follows. We take V2 divided by V1. In other words, the ending value divided by the starting value. Let's go ahead and do one last example. Suppose a population changes by a factor of 0.8 every 10 years. The current population size is 10,000 individuals. Complete the table below, and we will round all numbers to the nearest whole number. Let's look at the first row of this table first. It shows time in years since the current year. 0 here represents the current year. 10 represents 10 years after the current year. This is 20 years after the current year, 30 years after the current year, and 50 years out into the future. In the second row, we're going to record the changes, or not the changes, we're going to record the populations in those years. The first thing we want to do is calculate the population 10 years out. Well, we're looking at this first time period from 0 to 10. This is a 10-year period. We're told that this population changes by a factor of 0.8 every 10 years. The 10,000 here would be our starting value. We're trying to determine our ending value, namely the population in year 10. To calculate the ending value, we take our starting value and we multiply by 0.8. In other words, 10,000 times 0.8. This gives us 8,000. Now we want to calculate the size of the population 20 years out. From 10 to 20, we have another 10-year period. So again, the population will change by a factor of 0.8 during this period as well. In this case, however, the 8,000 in year 10, that's our starting value. That's V1. We're trying to determine the population size in year 20. That's V2. To do this, we take our V1, our 8,000, and we multiply by 0.8 again. When we do this, we get 6,400. That's our ending value. Now we want to determine the size of the population in year 30. From 20 to 30, that's another 10-year period. So again, the population will change by a factor of 0.8. Our starting value is 6,400. Our ending value is the population in year 30. We're going to take our 6,400 and multiply by 0.8 to get our ending value. When we do that, we arrive at 5,120. Now we want to determine the size of the population in year 50. If we look at this time period, our final time period, from 30 to 50, we notice a change here. It's not another 10-year period, but rather a 20-year period. So what happens during this 20-year period? You can think of 20 years as being broken down into a first 10-year period and then a second 10-year period. Over the first 10-year period, the population changed by a factor of 0.8. So just to go out 10 more years, we multiply by 0.8. But we need to go out yet another 10 years past that, which means we're going to have to multiply by yet another 0.8. So multiplying by 0.8 twice will enable us to go out 20 years. Multiplying by 0.8 two times means we're really just multiplying by 0.8 squared, or if I multiply this out, 0.64. So if I take my starting value, which in this case would be 5,120, and I multiply that by 0.64, that should tell me the final value of the population 20 years out. If I calculate this, I arrive at 3,277 when rounded to the nearest whole number.